Students, this is KG Misra. I'm here again with the next part of the video, that is second part of chapter electric potential and capacitance of class 12th. I hope all of you are well and fine and all of you are putting your hard work in your studies. Okay, let us start. In last video we have discussed about the electric potential due to a point charge, okay, and lots of point charges. And we are already aware of the electric field. Now, how they vary with the distance? Let us start with a graph. This is x-axis. This is obviously your y-axis, okay, and this is the origin. Here you have taken the electric field and potential both, okay, and here it is the distance, okay, like 1, okay, then 2 meter, then 3 meter, and then 4 meter. It's like that, okay. What we find, potential decreases like this, slowly, and then okay, like this, okay, decreases. Sorry, this part first it is decreasing like this, and then it is going like this, okay, decreasing. Now this is the electric field which goes like this and this. Okay. So this is your electric field and this is your potential. Potential, we know it is what? It is kq by r. And what is this? This is kq by r square. Okay. So what happens? See, initially what you will find when distance is less than 1 meter. Then you will find, no, it is less than 1 meter means it is 0.5. Okay. So suppose kq, suppose let us take kq is equals to 5. Okay. So it will 5 here as well as here. Here you are putting, suppose it is 0.2. So 0.2. How much you will get? You can write it 50 by 2, that is 25. What about electric field? You will write 5 by 0.2 square. Okay. So what will happen? See, you will get 5 by 0.2 square is 0.04. That means how much? You can write 500 by 4. Okay. 500 by 4 is how much? It is 125. Okay. So which is more? Electric field is more. And that's why corresponding to the same distance, you will find electric field is more initially. Okay. When distance is less than 1. And at distance 1 meter, what you find? The potential and electric field is same. When the distance is same, 1 meter for both and for the same charge. But as you move ahead, distance, you keep on increasing the distance. What you find? You find that the electric field decreases rapidly than the potential. Why? Because you know, electric field E is, you can see from here, E is proportional to 1 by r square. That's why. Okay. Whereas potential you can say it is proportional to 1 by r. So this is the graph of electric field and electric potential versus r. Here you can write V oblique E. Okay. Both are there. So I think you have understood this. Okay. Our next topic is electric potential due to an electric dipole. Okay. So we are going to find out the electric potential due to an electric dipole at what point? At axial point. Okay. So see here, this is our electric dipole. Suppose this is minus q charge, this is plus q charge. Okay. Separation is 2a as usual. This is the axis of this dipole. On this axis, suppose here we have chosen a point P. Okay. On this point, we have to find out the electric potential. Now, for this, let us name this dipole as AB, and this, let us name its center as C, because always we take the distance of the point from center. Okay. Let distance is R. Okay. So we have to find out the electric potential at point P, okay, which is lying on the axis and at a distance R from the center of the dipole. Now, if this is the center, then this distance is how much? A. And what about this? This is also A. Okay. Now, first we will find the potential due to charge which is there at A. Okay. That is VA. So VA is how much? It is K. Q is minus. So minus KQ we will write. Minus KQ upon distance from here to P. It is R plus A. So R plus A we will write. What about the potential due to the charge which is placed at B at point P? So potential at point P due to the charge placed at B, we can write it is K. Q is positive upon it is R, and you have to subtract A to get this distance. So R minus A will give this. So R minus A. That's what we are getting. Now what is the total potential at point P? So total potential at point P is equals to, we can write VA plus VB. It is scalar quantity. We can simply add them. So minus KQ upon R plus A plus KQ by R minus A. That's what we get. Can we take KQ common? Oh, okay. We can take KQ common. We are left with minus 1 by R plus A plus 1 by R minus A. We are left with this. Okay. So what we can do? Vp is equals to KQ. We have to take the LCM. If we take the LCM, what we will get? R plus A into R minus A. Okay. And this R minus A will be multiplied with minus 1. So what will we get? Minus R plus A. And this R plus A we have to multiply with plus 1. So we will get R plus A. That's what we are going to get. Now what will happen? This minus R and plus R will cancel out. We will have A plus A, that is 2A. Okay. So what we are going to get finally, I think you have done. Do this first so that I can rub this. Okay, done? Okay. So I'm going to rub this now. Only the last part I will leave. Okay. Now see, Vp is what? It is K, Q, A plus A is 2A upon, this is C, R plus A into R minus A. That is A plus B into A minus B. So it is R square minus A square. That's what we are going to get. Okay. Now see, what is, can we write it like this? It is K 2AQ upon R square minus A square. Any problem in this? No. But what is 2AQ? It is equals to electric dipole moment P. So what we can write here? Can we write Vp is equals to 1 by 4 pi epsilon naught, rather for free space, okay? P upon R square minus A square. This is the expression for electric potential at an axial point. Okay, this is the expression for electric potential at an axial point. Okay, now we have to find the electric potential due to an electric dipole at an equatorial point. So let us go for that. I should rub this, I think. You have done? Okay. Now we will find the electric potential at an equatorial point. So it is B part at an equatorial point. See, this is the dipole. Minus Q, it is plus Q. Distance is 2A. Equatorial point means perpendicular bisector of this. Okay. This distance I am taking here point P, and this point P is at a distance R. Okay. Now let us join this. What is this? This is A and this is A. So this will be how much? Square root of A square plus R square. If we join this, again this distance is A square plus R square. Square root of that. Okay. Now we have to find out the potential. Now let us mark this A and B. So charge which is at point A will have its potential at point P is equals to how much? We can write the formula. V A is equals to this K minus Q is there. Okay. Upon distance is how much? Square root of A square plus R square. Okay. What about the potential due to the charge at B at point P? It is K Q upon square root of A square plus R square. Okay. Now, what is the net potential at point P? Net potential is how much? It is equatorial. Okay. So we can write simply VA plus VB because it is scalar quantity. Now when we are writing VA, we will get minus KQ upon A square plus R square. Okay. And here what we will get? KQ A square plus R square. You are going to get 0. So electric potential at an equatorial point is 0 for an electric dipole. Now see, just note it down. Note it down. Okay. See, this equatorial, I have taken R is arbitrary, no? We have not taken any fixed value. So R, this point can be here, 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 or anywhere on this line. Okay. So that means if on this whole line the potential is 0. Now, if you are taking lines parallel to this, then on those lines also the potential will be 0. So you will get a plane, okay, which is perpendicular to this line and passing through this, okay. Now, on this plane also you will find the electric potential is 0, okay. So that this type of plane, no, on which the potential is same throughout, we call it equipotential surface, okay. So potential is 0 and it is same, so it is an equipotential surface, okay. Okay, we will discuss this equipotential surface in more detail. Okay. Now, the third one, we have to find out electric potential due to an electric dipole at an arbitrary point, okay, at a general point, okay. We have to find out electric potential at a general point. Now see, this is our dipole. This is minus Q, this is plus Q, this separation is 2A, okay, and we have chosen a point here. This is our point P. So let us join this. Okay. Let this distance be R1, this distance be R2. Okay. At the same time, from center, this is A, this is B, and from center let it point C. Okay. We have to join this point. Okay. Let this distance is R and this angle is theta. Okay. This much we have taken. So this is the electric dipole and we are taking point here. It is not on the equatorial point and neither on the axial point. It is general point. Angle theta is given and this distance is R. R1 and R2 are not known. We have just taken for the time being. We have to replace it with R and theta. Okay. Now, what is the potential at point P due to the charge which is placed at point A? See, for that what we have to do? That is equals to K minus Q upon distance is R2. In the same way, what is the potential at point P due to the charge which is placed at point B? That is VB is equals to KQ upon R1. Okay. Now, what is the total potential at point P? Total potential at point P is equals to VA plus VB. Okay. Now, what we will get? Let's see. From here, we can write minus KQ upon R2 plus KQ upon R1. Okay. So from here what we can get? Can we take KQ common? KQ has been taken common. We have got, see, 1 by R1 is positive, 1 by R2 is negative. 1 by R2 with negative sign, 1 by R1 with positive sign. That's what we have got. Now what we can do? See, Vp is equals to KQ is common. We can take the LCM. We will get R1, R2. Okay. And what will get in the numerator? This minus 1 into R1 is minus R1. R2 into plus 1 is plus R2. Okay. So we are left with this. Just write down so that I can remove and we can move ahead. All of you noted? Okay. Now I am going to rub this part, okay, so that we can get proper space to write. Now see here, Vp will be how much? It will be KQ. You can write in the simplified form, that is R2 minus R1 by R1 R2. This we got. Let us mark this equation number 1. Okay. According to geometry, if we draw a perpendicular from here to here, see this is perpendicular over here. Okay. So let us name it as D. Okay. This point is D. So according to geometry, what happens? If we are drawing perpendicular from here to here, then what will happen? This length is equals to R1. If this is R1, then this is what? This is difference of R1 and R2. So we can write this is what? This distance is R2 minus R1. Okay. Clear? Now, as this point is far away, so this angle will be approximately equal to this angle. So we can write here theta. And now, what is this length? 2a. If this is 2a, this is what? 2a cos theta. Okay. So what we can get from figure? From figure, R2 minus R1 is equals to 2a cos theta. Now, we have got the value of this. What about this? Because R1, R2 is not known. Now see, for this what we will do? R1, R2 is approximately equals to R square. How can we say that? See, we will use the numbers to do this, okay? Suppose you have got numbers like 3, 4 and 5, okay? What is 4 square? It is 16. 5 3 are 15. So 15 is very near to 16 or not? There is a difference of only 1. So this happens. Because see, middle number, it is R. Square of this we have taken here. Okay. The larger number, that is R2. Okay. The smaller number is 3. That is R1. Okay. So product of 5 and 3 is 15 and product of 4 is 16. So approximately equal I am writing. Actually just we have taken the example to understand this. Okay. It's not that there will be a difference of 1. Very small difference is there between the distances. Because this dipole is very small as compared to this distance. Okay. So we can write this. Now after this approximation, what will happen to our equation 1? So you can do one thing. You can mark this as equation number 2. So you will write from equation 1 and 2. What will get? Vp is equals to K Q. At the place of R2 minus R1 you will write 2a cos theta upon R. At the place of R1 and R2 you will write R square. So this is the expression for electric potential due to an electric dipole at a general point. Now suppose you want to find out the electric potential at the equatorial point. Before that, we have to convert this 2aq into P. We can do that. Okay. So what we'll get? We'll get Vp is equals to, that is K is 1 by 4 pi epsilon naught. 2aq is P and cos theta is cos theta upon R square. Okay. This expression we get. Okay, this is our final expression. Now, this is very important expression. How? This is for general point, but if suppose you want to find out at axial point. So this point P will come over here. Now, when this point comes here, this angle will be 0 degree. Just keep here 0 degree. Cos 0 is how much? 1. So what you will get? 1 by 4 pi epsilon naught P by R square. That was the expression for axial. Okay. Now let's suppose you want to find out for equatorial. For equatorial, this angle will become how much? 90 degree. Put there 90. Cos 90 is how much? 0. 0 into something? 0. So potential is 0 at equatorial point. And this way you can find out for any angle. And that's why we have derived this. Okay. In case of electric potential due to a point charge, we have seen that V is proportional to 1 by R. Because see, we have got the formula now, V is equals to KQ by R. What about the case of dipole? We have seen that it is K P upon, okay, that is 2P, we can write, okay, KP cos theta upon r square was there. That means we can say that V is proportional to 1 by r square. Okay. So this is the comparison actually for the potential in case of point charge and in case of dipole. Okay. So it is decreasing more faster than this because see here you find r square. Okay. Our next topic is relation between electric potential and electric field. See, when we are talking about the relation between electric potential and electric field, we have to study minutely the electric field. See, when we are saying that there is a uniform electric field, okay, which is represented by parallel and equispaced lines, okay, like this. Okay. So there are certain things which we are not representing over here. What is that? We know that these lines come out of positive charge. That means there somewhere we have got array of positive charges. Only then this is possible. And here is array of somewhere there is array of negative charges. Okay. Suppose this total charge is Q and this total charge is minus Q. Okay. Now what will happen? If you find the potential somewhere here, very near to this. Okay. Suppose the distance is very small. Okay. Let it be R. Okay. And this distance is suppose D. Okay. So, what will the potential at this point? This distance is D means this distance is D. Okay. So, what will the potential at this point? Let's find out. So, potential at this point, you need not to write, just try to understand. Potential at this point will be how much? It will be K, Q by R, okay, plus, rather minus because charge is negative, minus KQ by D. Okay. Now, which has got the more value? Obviously, you can write this like this, KQ 1 by R minus 1 by D. As D is longer than R, so 1 by D is smaller than 1 by R. Not getting? Very nice. You know 10 is greater than 2. But what about 1 by 10 and 1 by 2? 1 by 10 is 0.1. 1 by 2 is 0.5. Now which is larger? The sign has reversed. Okay. In the same way, D is larger than R, but when you are doing 1 by, then 1 by R is greater than 1 by D. So this is going to become positive. That means potential near this area of charge is positive. Now if you take this here, suppose a point is here which is at distance R from here, and from here it is distance is D, obviously. Okay. Then what is the potential at that point? Let us see what is the potential at that point. V is equals to KQ upon, this is D, okay, minus KQ upon R, okay, at this point. Now what will happen? See, KQ we can take common. We will have 1 by D minus 1 by R. Now tell me, D is longer than R. Okay. So this is smaller than this. Now when this is smaller than this, what will happen? 1 by D is smaller than 1 by R. That means this is going to be negative because 1 by R is greater than 1 by D. So this is going to be negative. That means potential near this area of charge is negative. What does this indicates? This indicates that as we move from here to there, okay, you can see from here also, R will increase. As R will increase, this value will decrease. As this value will decrease, see, this D will decrease, because when you are increasing R, D is going to decrease. As D will decrease, this value will increase. So as this is increasing and this is going to decrease, as you are moving that side, what will happen? A point of time will come when this will be larger than this. So their potential will become negative. That means the summary is that when you are trying to move from side of positive area of charges towards the area, negative area of charges along the electric field, then your potential is positive first, then it decreases gradually, okay, becomes 0 and then becomes negative. Okay, it cannot become positive to negative suddenly. Okay, gradual decreases there from positive to negative. What does it mean? Potential decreases when we move along the direction of electric field. That is the first thing we get from here. So under this heading, you write first thing, as we move along the direction of electric field, the potential decreases gradually from positive value to negative value. Written? Okay, very nice. The potential decreases gradually from positive value to negative value. Okay. So see, as we know that potential decreases when we move along the direction of electric field. So see, this is the direction of electric field intensity, okay? And we have selected two planes. These planes are very closely spaced. Suppose potential at this plane is V. So what about the potential at this plane? It will be less than, little bit less than that, very less than that. So we can write V minus dV. Okay. Now what is the potential difference between these plates? So potential difference between these plates is potential difference is how much? It is V minus dV minus V, and that is how much? Minus dV you get. That is the difference, potential difference. Now, in order to achieve this potential difference, how much you have to move along the direction of electric field? dr distance. So what is the rate of change of potential with respect to distance when you are moving along the electric field? So right, therefore rate of change of potential difference, rate of change of potential, not potential difference, rate of change of potential with respect to distance along the direction of electric field is, it is given minus dV upon dr. Okay. This is there. Okay. And this is rate of change of potential with distance, that is called, that is equals to electric field intensity. Okay, in that region. This we can get. Or we can write this like this, E is equals to minus dV by dr. This minus indicates that when we are moving along the direction of electric field, then the potential decreases. Okay. You might be thinking, why sir has kept this electric field? I will tell you, don't worry. Okay, just note it down, then I will explain you. Done? Okay. See, suppose we know very well one thing. What is the relation between electric field and a force? Suppose you want to take a charge. Okay. Suppose a positive charge you are keeping in an electric field E. Okay. Here Q charge is there. So obviously it will move with the electric field. And suppose you want to take it in the backward direction. So what you have to do? You have to apply the force equal to the force applied by this electric field. How much force this electric field is applying? It is applying F is equals to QE. This much force it is applying. So how much you have to apply? You have to apply a force equal to minus QE. Okay. This much force you have to apply. Okay. Now, so force you are applying is how much? That is equals to minus QE. Now, suppose you are moving it by a distance dr. Then what is the work done? Work done is, that is F dr, and that is equals to minus QE dr. Okay, this is the work done. Okay, but we also know, this is our equation 1. We also know, what we know? Work done is equals to Q into V, where or Q into V, where V is the potential difference from class 10. So what you can write? Suppose this potential difference, so you can write V2 minus V1. That is more better way to write. As this potential is very less, because see, you have dragged very small distance, no? So between those 2 points, suppose you drag it from here to here, So between those 2 points, the potential difference will be very small. So what we can write? We can write Q dV. Okay. So work is Q dV as well as work is minus Q EDR. So we can equate both of them because both are work. So from 1 and 2, what we can write? Q dV is equals to minus Q E dr. Q can be cancelled out. Okay. So what we can write now? So we can be write from there, that is dV upon dr is equals to minus E, or we can write E is equals to minus dV by dr. Okay. In this way we got this relation. Okay. So this differentiation of potential with respect to distance. Okay. Now from here we can utilize this result to find lots of things like electric potential due to a charged sphere. Okay, charged sphere or spherical cell. Okay, conducting sphere or spherical cell. How can we find? Let's see. Suppose electric potential. Okay. See, electric potential due to charged thin spherical cell. This is spherical cell, very thin spherical cell, suppose. Very thin. Okay. And this is the center of the spherical cell. Let it be O. Its radius is capital R. Okay. This is the surface. Okay. And suppose you want to find out the electric potential on the surface. Okay. So, actually what happens in case of a spherical cell? When you are trying to find out the potential, we can suppose the whole charge to be concentrated at the center, and in that case the potential at the surface will be how much? It will be K Q, if the charge, total charge is Q, upon capital R. Okay. Now what about the potential inside? We know very well the electric field inside the spherical cell is how much? It is 0. This we know, we have found out using the Gauss law. And we also know that E is equals to minus dV by dr. So when this E is 0, that means dV by dr is equals to 0. When dV by dr is 0, you know differentiation of anything is 0 when that thing is constant. That means V is constant with R, that is distance. And where it is constant? Wherever the electric field is 0. So electric field is 0 inside. So inside, with the distance from the center, the potential is constant. That means what we find, the potential within the spherical cell everywhere, it is how much? It is got the same value. So V is equals to how much? It is KQ by R. Okay. Clear? Potential at the surface is how much? KQ by R. Okay. Now if you want to find out the electric potential at any point in this, inside this, then what we have to do? We know that electric field inside this is 0 by Gauss, application of Gauss law. Okay. And we also know E is equals to minus dV by dr. Now as E is 0, so we can write dV by dr is equal to 0. And this implies that V is equals to constant.